Hello, thank you for joining us for this presentation on preliminary anticipatory recovery impact assessments. My name is Scott Kaiser and I'm a senior GIS analyst with J&M Global Solutions based in Washington, D.C. My colleague presenting with me today is Joshua Barnes, the former National Recovery Coordinator with the U.S. Department of Health and Human Services. We are excited for you to join us today to talk a little bit about how we used a Geo Design Framework to better understand the public health impacts of three major hurricanes during the 2018 Atlantic hurricane season. And without further ado, I will turn it over to Josh to talk a little bit more about the background and why we used a Geo Design Framework and some of the problems we were seeking to solve. So with that, Josh, please take it away.
Good morning or good afternoon, depending on where you may be watching this presentation. Thanks for taking the time to learn more about the work that we did. To provide some context, one of the important things is to understand why we did this, and to help underpin that, just to review some quick background. Since roughly 2011, the federal departments and agencies have been required to implement recovery missions in a different way, and that's through the National Disaster Recovery Framework. The ultimate goal and objective of that framework is to better integrate the tools, resources, and capabilities and authorities that the different federal agencies have in order to support states and communities and tribes and territories after a major disaster. This, however, comes on top of what often is the case, has been the case in emergency management, where they saw themselves and taught themselves as that emergency management is a cycle where you have an incident followed by a response, followed by the recovery, followed by mitigation, and then you proceed back into preparedness until the next incident happens. But the inception of the National Disaster Recovery Framework changed that perspective such that it acknowledged that complex, wide-scale disasters really necessitate having a two-pathway approach or a tandem approach to implementing both response activities and recovery activities simultaneously. This is needed because oftentimes, while the response is dealing with life-saving and life-sustaining issues, there are other needs that the community has that are pressing, but may not be life-saving or life-sustaining, but are critical to its long-term recovery options. So this creates a problem where a lot of the resources and the data that's available to us on the response side of the equation is more easily modeled. It's readily identifiable and quantifiable. How much rain fell, how many buildings are damaged. You can articulate and identify that through remote sensing, through windshield surveys, through other data analyses. But the problem with analyzing recovery impacts is that they tend to be a lot more pervasive, but less intense. And so you can have a really substantial issue, but it's more of a low burn or a dull roar compared to the surge in intensity that you would have with the response need. So we have had this issue where how do we then best align agency resources working to support the states and the communities in a similar way that we do with the response, but also for the recovery. If it's difficult to discern and define where exactly that recovery need is going to be manifest to flood risk, area building code standards, and the like, we also do know where we have key assets for the community pre-incident. So things like hospitals, childcare centers, elder care facilities, skilled nursing facilities, and we know where those key assets are located pre-incident. And so once we start to layer what we can expect out of the hazard, expect out of how that hazard will impact the vulnerabilities that we know that exist, and the potential impact to those facilities that are located in the area, we can begin to then take what we know about what happens in recovery long term and begin to extrapolate what are some of the potential impacts based on that analysis. And now I will turn the presentation over to Scott. Scott, take it away.
Thanks, Josh. So we set out to establish a geodesign framework and method to evaluate the known hazard values. For example, observed rainfall, storm surge models, measurable wind speeds, etc., to evaluate potential consequences to public health infrastructure, both before, during, and after hurricanes. We call this approach or this framework the Preliminary Anticipatory Recovery Impact Assessments. The framework is intended to be rooted in GIS, but flexible, repeatable, and scalable, and relies entirely on publicly available data. We often observe these types of impact analyses in the form of hazard mitigation plans or other pre-disaster planning initiatives. But prior to this work, we were not aware of a framework for evaluating preliminary impact on public health infrastructure based on real-world outcomes as events are unfolding. So by leveraging the power of ArcGIS Pro with the Spatial Analyst Extension, we used a variety of reclassification and weighted overlay methodologies to evaluate the regional impacts. So that is the storm forecasts and the observations. From there, we then tried to classify county risks. So the idea of taking a weather system as large as a hurricane that in many times can span multiple states, how do we narrow that focus down to understand what is the true impact, what is the true magnitude of impact, and we do that through sort of a classifying the county risk approach, where then we can identify where resources are really going to be necessary based on the impact. And then from identifying the county risk, we can then assess the public health infrastructure within these high-risk counties. And the framework is designed to be rerun by analysts during the course of the event as new forecasts are issued and observed data becomes available. So we applied this framework across 3 different storms during the 2018 hurricane season. Hurricane Lane made a pass by the Hawaiian Islands. Hurricane Florence made landfall along the North and South Carolina coast, and Hurricane Michael made landfall along the Florida Panhandle. You can see each of the inputs that we had into our analyses. One of the common ones was the 7-day estimated rainfall forecast, and you can see based on this table that it was a pretty wide range, anywhere from 5 to 7 inches from Hurricane Michael to north of 30 inches in Hawaii from Hurricane Lane. And one of the important takeaways of this particular table is we need to evaluate each storm as its own individual system, rather than trying to identify opportunities to use lowest common denominators to apply across all types of storms and weather systems. So we'll start with Hurricane Florence. This was the second major storm in the 2018 Atlantic hurricane season. The storm tracked fairly close to North and South Carolina over the course of several days, and then proceeded to just park itself over really the border between North and South Carolina and continued to dump a tremendous amount of rain over the region. So one of the first things that we did was try to understand what the coastal storm surge was going to be and what it was forecasted for this particular storm. And we were able to do that on a county-specific level using the forecasts that were issued by NOAA and other government weather agencies. And then in this particular storm, we evaluated a threshold of 10 feet or greater and then 1 to 6 feet of storm surge based on those forecasts. And you can see that in the map here that's outlined, identifying areas that are at greater risk for the 10-foot storm surge versus areas along the coast that storm surge was not going to be nearly as severe. We then added the observed precipitation over the course of 7 days. And you can see that we've got areas of extreme rainfall, 20 plus inches of rain, but we also have widespread areas of 15 to 19 inches and 10 to 14 inches. Because of the amount of rain that was falling on this particular region, we knew riverine flooding was going to be a major concern. And so we used the network of USGS stream gauge sensors to understand which sections and portions of rivers along the Carolinas were expected to reach and exceed the flood stage. And in this particular case, we were looking for the location of what was classified by the USGS as major flooding events. We can then combine all of these inputs to understand what counties are at greater risk for high impact to health and social services. And that's what you see highlighted in the salmon color underneath all these various layers. So this essentially identified the high risk counties for us, and then we can then dive further into understanding what the health and social service impacts would be within these counties. From here, we were able to look even more closely at individual zip codes, and we can identify areas that actually flooded, both from aerial and riverine, as well as storm surge. And that's the red that you see scattered across the map. And we can add that in again with the flood hazard zones from FEMA, and the preliminary storm surge is factored in here as well. We can then add some social demographic data. So looking at Medicare and Medicaid beneficiaries, we can identify zip codes that have a greater than 25% of the population are Medicare and Medicaid beneficiaries. And that gives us an idea of the socially vulnerable populations that might be at greatest risk of these impacts in the region. And then we can add our public health and social services infrastructure, and through some analysis based on location as it relates to our high impact zones, we can get an understanding of how many facilities are actually at risk. And this is just another example of a particular area along the coast that suffered some pretty extreme impacts. So if we turn now to Hurricane Michael, this was the second storm of the 2018 hurricane season. In this particular storm, this was actually less of a rain event and more of a coastal surge and wind event. The storm was rapidly intensified as it approached the coast, which was a little bit unexpected, but it moved so quickly that there wasn't an opportunity for rainfall to really fall widespread across the region like we saw with Hurricane Florence. This storm acted like one big giant tornado, if you will. So storm surge was pretty significant along the coast, particularly in Bay County. We have overlaid observed precipitation, but in this case, this was a limiting factor. It wasn't nearly as crucial to the overall analysis, but we had a threshold of 7 inches or greater, and then areas that received 5 to 6 inches of rain. And then, of course, because this was such an extreme wind event, we overlaid extreme wind warnings that were issued by the National Weather Service throughout the duration of the storm. And their definition, their threshold for extreme wind warnings is greater than 115 miles per hour sustained. So a massive amount of force is behind these winds. These were the counties that experienced an extreme wind warning at some point during the landfall of Hurricane Michael. And again, we can add these things on top of each other to understand which counties are the high-risk counties. In this case, not as many as we saw in Hurricane Florence. So it narrowed our focus a little bit more. And when we went to add the other social demographic information and the public health infrastructure, we had a fairly good understanding of what the impacts might be, particularly in Bay County, which was hardest hit. And this is just the aftermath of one of the regional hospitals. You can see the widespread devastation to the neighborhood surrounding it, but also to the physical structure of the hospital as well. And then finally, Hurricane Lane. This was actually the first storm that we applied this methodology to, but one of the surprising things that surprised us during this was just how much geography factors in to how impactful a storm might be. In this particular case, the storm actually tracked and never made landfall in Hawaii, but because it was tracking to the southwest, that meant that the Hawaii Islands were actually in probably the worst quadrant of hurricane systems, that being sort of the northeast quadrant where you get all of the rainfall and some of the strongest winds. Again, using the same methodology where we applied multiple factors, we looked at rainfall, not only from the widespread forecast, but also from actual rain gauge collection. We saw areas that actually almost reached 50 inches of rain, which is pretty incredible. But the overall impact was actually pretty minimal to infrastructure because of the topography of the Hawaiian Islands, where a lot of this water just ran right off the island directly into the ocean and didn't actually have time to overflow riverbanks and affect larger portions of developed areas. So some of the key findings: understanding topography and storm characteristics are as important as knowing the location of critical infrastructure, and the combination of all three factors can provide a basis for organizational decision making, in some cases in near real time. When applied to prior to and during a forecasted event, geodesign is an effective model to evaluate the location and magnitude of impact to public health infrastructure. And our methodology and framework is easily replicable. Using common scripting tools, this approach can be automated and integrated into existing organizational decision-making processes. All of our data sources in our analysis are all publicly available, and many of them have open APIs, which means you can stream this data directly into your applications, and you can iterate through this process however many times you need to be able to make decisions throughout a particular event.
Thank you, Scott, for going through all that content so quickly and so thoroughly. There's a lot of information there. So bringing this all to a close, one of the things that we found that's really important and really useful is that we were able to use this approach to identify ways to concentrate and focus resources and assets and ask questions about what's going on in a given area where we may anticipate there's going to be needs, so that we're not waiting for a disaster survivor or disaster impacted community to come tell us that they have a problem or a challenge, but we can go to them and say, hey, based on the data, based on the modeling, based on what our information is suggesting, you may have a need. How can we be supportive of that need and fill that gap? So having that reliable hazard-specific vulnerability variables is exceptionally valuable to provide this actionable information to direct resources, both for the recovery and, of course, also for the response. Something else that we learned was that having local insights about which variables to define the vulnerability and the impacts make for better indicators, so that they have a sense for what are those things that are going to be a tipping point, things that are going to be a good trigger to signal when there's going to be major disruptions in the services that are provided by key community assets. And ultimately, when we're looking at identifying the recovery impacts, those are still going to be manifest in the weeks and months after an incident. But by being able to prioritize both the resources going into an area, but then also prioritizing our attention and looking at an area to ask the critical questions at the right time, we can have the opportunity to provide more timely and more effective support to those areas that have both high vulnerability and high impact as soon as humanly possible. So thank you, and thank you for taking the time for today's presentation, and we hope you are able to take some of the lessons and apply them in your settings wherever you may be. Thanks.